Okay, so here is our lecture video for section 10.4, used inscribed angles and polygons. So to start things off, we got some new definitions that we have not seen before. Our first one is an inscribed angle, which is an angle whose vertex is on a circle and whose sides contain chords of the circle. So basically it's an angle created anywhere inside the circle where the tip of the angle is on the edge and it has two chords extending out. And our next definition is an intercepted arc, which is the arc that lies in the interior of an inscribed angle and has endpoints on the angle. So looking at the picture down here, we have our inscribed angle and the sides of the angle extend out here. The arc that's created where these two endpoints are, we call it our intercepted arc. So those definitions help us make sense of our first theorem here, our inscribed angle theorem. And this one tells us that the measure of an inscribed angle is 1/2 the measure of the intercepted arc. So it's 1/2 the measure of the intercepted arc. So over here, our inscribed angle would be angle D right here because it's created by these two chords and it's on the edge of the circle. And we would know that that measure of the angle is 1/2 the measure of this arc AB right here. So let's see what this looks like with some numbers in an example. Find the indicated measure and circle P. So the first thing they want us to find is the measure of angle T. Well, they're talking about this angle right here because that's our inscribed angle. And if we think about it, if we extend the sides of the angle to see where the intercepted arc is, it's the arc between R and S, which is 48. So we know that the measure of angle T is going to be half of that. So 1/2 of 48 is 24. So we can think of it dividing by 2, multiplying by 1/2. So then if we're looking at part B over here, find the measure of arc QR. Well, arc QR is this guy right here in pink. What I'm highlighting in pink is arc QR. As of now, we don't really know anything to just tell us that right away, but let's see if we can piece a few things together. Something that we're probably going to end up using is this 50 degrees right here because it's given to us, so we're probably going to use it. And we can see that this 50 degrees is the measure of this inscribed angle, which means if we look at its intercepted arc, which would be QT, right here, we know that that angle is 1/2 the measure of this arc, QT. Well, 50 times 2 is 100. So we know that from Q to T is 100 degrees. The measure of that arc is 100 degrees. Well, if we look at the circle, they give us center P, which means that the segment RT right here is the diameter because it goes through the center. It's a chord that goes through the center. It's a diameter, which means it splits the circle into two semicircles, which means this entire arc right here all together from T to Q and from Q to R is 180 degrees. And since we know that QT is 100 degrees, we can do 180 minus 100 to get that. This leftover piece from Q to R is just going to be 80. And that's kind of piecing that together. So remember, the measure of the inscribed angle is half the measure of the intercepted arc. So if we keep moving forward, things get a little bit more complex. For example 2, we want to find the measure of arc RS and the measure of angle STR. And then what do we notice about it? So we're going to make some observations. So looking at this picture right here, they tell me that angle U is 31 degrees, which means that arc SR is going to be double that. So we know that 31 times 2 is going to give us 62 degrees. So that arc SR is 62 degrees. And that's the first part right here. So that's the first part of the question. And then measure of angle STR, well, STR, that's this angle right here. Again, angle T is an inscribed angle, so let's see what its arc measurement is. If we kind of extend the angle out, we see that it's actually the same arc as angle U down here. It's still just arc RS, which is 62 degrees, and we know that the measure of angle T is going to be half of that. To get that, it's 31 degrees. So it ended up being the same. So what did we notice about it? We noticed it's the same as this inscribed angle over here. And what these two angles had in common is that they shared the same arc. And this observation leads us to our next theorem. If two inscribed angles of a circle intercept the same arc, then the angles are congruent, which is exactly what we just saw. So looking at this picture over here, angle D right here has arc AB, and angle C, if we extend these chords, is also arc AB, which means those two inscribed angles are going to be congruent. So let's take a look at some type of multiple choice questions we might see with this. Name two pairs of congruent angles in the figure. So before I even jump in to just looking at the list, I'm going to go ahead and mark up my picture over here so I know what angles will be congruent. Looking at this picture, I see angle K. I look to see where its intercepted arc would be, and it's JM. Well, angle L also shares that same intercepted arc, so I know that K and L are going to be congruent. And then looking at angle J, we switch directions, we have opposite sides, so angle J has the intercepted arc of KL, and so does angle M. They share those arcs. So we marked which angles are going to be congruent there. So now we just need to go through our list over here. So angle JKM, so angle K is congruent to KJL, KJL. So is angle K congruent to angle J? No, not right. Angle JLM, angle L is congruent to angle KJL, KJL. Is angle L congruent to angle J? No, not right. JKM, angle K is congruent to JLM, angle L, that's true. KJL, angle J, KML, angle M, that's also true. C is our answer. So that's kind of an example of what a multiple choice question might look like. So why don't you guys go ahead and pause the video and see if you can figure out these three examples on your own. These are going to be more typical of what you're going to see. Come back when you're ready to check your answer. Okay, so number one, find the measure of the angle or the arc. So number one, they want us to find the angle, the inscribed angle, so we know it's going to be half of that arc. So 90 divided by 2 is going to be 45 degrees. Number two, they gave us the angle, so we know that that angle is half of its intercepted arc. So to get the arc, we would multiply by 2 to get 76 degrees. And over here, they gave us one inscribed angle and wanted us to find the other. Well, the arc for both of these inscribed angles is a shared arc, so we know that that is also going to be 72 degrees because they share the same arc. So they will be congruent angles. So hopefully you guys piece together through that one okay. We're going to keep moving forward. We have a few more definitions to get us through here. Second half of the section. An inscribed polygon is when we have a polygon, so a shape, where all of its vertices lie on the circle. The circumscribed circle is the circle that contains all the vertices. So breaking down these words, inscribed polygon, inscribed, we think inside, circle. Circumscribed circle is the circle that goes around it. So looking at our pictures, we have two inscribed polygons here because there's a circle that goes around it that connects all the vertices. See how this circle connects every single vertex of the shape? That's what it means to be an inscribed polygon. And we need to know this because our next theorem here, let me focus the camera. Okay, the next theorem says, if a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. So if a right triangle is inscribed in a circle, so right triangle, inscribe the circle, inside the circle, the hypotenuse is the diameter. And the converse of that, if one side of an inscribed triangle is a diameter of the circle, then the triangle is a right triangle. And the angle opposite the diameter is the right angle. So we're working again with right triangles inside circles. If we know it's a right triangle, the hypotenuse will be the diameter. If we see that one side of the triangle is a diameter, then we know it's a right triangle using both the theorem and its converse. So let's do more of a thinking example to kind of see how this would work. So say your camera has a 90-degree field of vision and you want to photograph the front of a statue. You move to a spot where the statue is the only thing captured in the picture. It's the only thing you see as shown. You want to change your position. Where else can you stand so that the statue is perfectly framed this way? So basically you want the statue to be the diameter of your circle. So you can't see anything around it. It fills up the entire half of the circle, which is shown here. So if this guy is our diameter, the face of this statue, we can think of a circle surrounding it where it's the diameter. And it's okay, so I'm just going to sketch a little circle here. So where could you move so that that remains the diameter? Well, we know that if we have a inscribed right triangle, that the hypotenuse is always the diameter. So basically, this point right here where you're standing, you can move it anywhere along this circle. Like say you're attached to a string here and you can only go along this circle, and wherever a right angle is created, that's where you could stand. And again, I'm just kind of sketching in some things here. Whoops. And it looks rough, but it's okay. You guys will get the idea. This is more of a thinking about it question, but basically wherever you can create that 90-degree angle, that face of the statue will be your diameter. Again, so that's more of a think about it type question. You guys aren't going to have to be able to draw that and explain that on your own. But if we were to kind of extend that here, thinking of the same example, explain how you find locations if you want the frame, the front and left side of the statue in your picture. Basically, you would just want to make the diameter of the circle the diagonal of the rectangular base. So basically, you would just change your diameter. So if we look back at this picture, you can kind of change your diameter to look something like that, and that would change the angle of what it wants. Again, these are more just kind of thinking about it problems, seeing if you guys understand the thought process behind it and what you can do. When it comes to like problems you're going to have to do on your own, they're going to be more math heavy, like we're going to see moving forward. So we're going to keep moving on. Still talking about inscribed quadrilaterals. Now we're moving on from an inscribed triangle to inscribed quadrilaterals, and our theorem for this one is a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary, and we know that long word right there, supplementary, means they add to be 180 degrees. So opposite angles are supplementary. They add to be 180 degrees. I think you guys are going to like these types of problems a lot better. They're very straightforward. So example 5, find the value of each variable. Well, they're inscribed in a circle, so we know opposite angles are supplementary. So for x, we know that x is going to equal 180 minus 80, because we're looking at opposite angles, to get that x is 100 degrees. And we're going to do the same idea with y. They're opposite angles, so they're supplementary, so y equals 180 minus 75 to get 105 degrees. Same idea over here. The math just gets a little bit harder. Still an inscribed quadrilateral, so opposite angles are supplementary. So if we're solving for A, those are our opposite angles right here. We know that 2A plus 2A equals 180. If we combine like terms here, we get 4A equals 180. Divide by 4 to get that A equals 45. And then same idea for B. We have 4B plus 2B equals 180. Combine like terms to get 6B equals 180. Divide by 6 to get that B is 30. Much more straightforward, just kind of solving for a variable. Again, inscribed quadrilateral, opposite angles are going to be supplementary. They add to be 180 degrees. So to wrap things up here, pause the video, try these guys on your own, come back when you're ready to check your answers. Alright, so opposite angles are supplementary, so looking at our x's here, we know that those two guys are going to be opposite angles, so we know that x equals 180 minus 82, so x is going to be 98 degrees, and then kind of the same idea for y, opposite of the 68, so y equals 180 minus 68 to give us 112 degrees. For number 6, it's a little bit more difficult, but still not too bad. Let's start with our x's here. Those two are opposite angles here involving the x, and we know that 8x plus 10x is going to equal 180. Combine like terms to get that 18x equals 180. Divide by 18 to get that x equals 10. And then to wrap things up here, to solve for c, we have that c plus 2c minus 6 is going to equal 180. Combine like terms, c plus 2c is going to be 3c minus 6 equals 180. Add 6 to both sides, we get 3c equals 186. Last but not least, divide both sides by 3 to get that c equals 62 degrees. So again, opposite angles are supplementary for an inscribed quadrilateral. That means we have the quadrilateral with the circle around it connecting all of the vertices. So your homework for this section is below. Honors, you're doing page 666, number 3 through 17. You're just doing the odds. And college prep, same page, 3 through 15. And again, still just doing the odds. Email me if you have any questions. And thanks for watching the video.